Part D. A pair of stationary balls, both from SM, are sliding along a long, horizontal frictionless groove towards a third ball, also at mass small m, as shown in the following diagram. So they show the diagram A, B, is C. Both of these 4 meters per second. C stationary. All of these have mass m, which will make it easy because we can cancel that out straight away. Okay, and then it says, for a collision of a pair of objects, the coefficient of restitution, sigma, is calculated by sigma being the difference in velocities after the collision, so it's delta V after divided by the difference in velocities before, delta V before. And we're told that this is 0.4. This situation. So this is our, so we've still got momentum conservation in each collision, but this kind of replaces the kinetic energy being conserved a bit. So in this case we don't have kinetic energy conserved, but it's giving you that second equation. Show that there are just 3 collisions between the balls and the sum of the final velocities of the 3 balls is 8 meters per second. Actually, that last statement is obvious, isn't it? It's this momentum conservation. So, sum of 3 velocities is always 8 meters per second because their masses are the same. So if we sum up m times v1 plus m times v2 plus m times v3, we know that it's got to be 8 meters per second times m initially. v1 plus v2 plus v3 equals 8 meters per second. So I think they tick that up, that last bit very quickly. 3 collisions between the balls. And I guess what will happen, well, this one's going to hit that one. C is going to go that way. B is probably going to rebound a bit. It might not, it might continue on a small velocity. No, I think it will continue at small velocity because these are the same mass. Because if this were an elastic collision, B would be stationary and C would carry on. So if it were inelastic, they'd stick together and carry on. So B I'm sure is going to carry on a bit, but at a smaller velocity. So then A is going to catch up B, hit B, and then they'll both carry on and B catch up with C. I don't know. Anyway, we'll work through it, I think. They've got a lot of lines for this one, which might hint that there are a lot of calculations to do. Okay, so first, for sure, B is going to hit C. Right, B hits C. So, momentum tells us that afterwards VB plus VC is 4 meters per second. We don't have to worry about the m's. The m's are all the same, so they're going to cancel. Okay, that's your first equation. Remember, we always need another equation, so this comes from, it's got to come from here, that extra bit of information. So the change in velocities afterwards, I'll difference in velocities divided by difference before is 0.4. So that tells us delta V after is 0.4 times delta V before. So that's 0.4 times 4 meters per second. What it was before, so that's 1.6 meters per second is my delta V. So that's going to be, VC is going to have a higher velocity, so that's VC minus VB is 1.6. So add them together, I get 4. Subtract them, I get 1.6. So 1 minus 1.6 is 2.4. Half that is 1.2. So VB is 1.2 meters per second. VC is my 1.2 plus my 1.6. 2.8 meters per second. So sum is 4. The difference is 1.6, which is 0.4 times over 4. Okay, so that's my guess, and then we can add VA is still 4 meters per second. So now we've got A rolling that way at 4 meters per second. B is chugging along at 1.2 meters per second, and C is moving at 2.8 meters per second. So, well, those two are separating. So A is going to come and hit B. So A hits B next. So that's our second collision. And I guess we just go through all that before. What happens? So, momentum tells us that afterwards VA plus VB is that plus that is 5.2 meters per second, and our restitution tells us that the delta V after is 0.4 times delta V before, and the difference is 2.8. 2.8, yep. So that's 4 minus 1.2. So that's 2.8. So 0.4 minus 2.8, 8.96. 1.12. Is that right?
I can do a quick calculation. My brain's
80, 32, 1.12 meters per second. Okay, so that means take my 2, if I add them, I'm going to get 5.2. If I subtract them, I'm going to get 1.12. That's right. So can't do that in my head, I forgot. So again, VB will be moving quicker after the collision. So minus VA plus VB equals 1.12 meters per second. Add and divide by 2 will get me VB. So VB is half of 6.32. So that's 3.16. That one minus that divided by 2 gives me VA, so that's 4.08 divided by 2.08 meters per second. It's 0.04. So it's 5.20, 1.12 difference. Yeah. Okay, so we now have, go that way, so A is moving at 2.04 meters per second, B is 3.16, C is still 2.8 meters per second. Okay, so next thing is B hits C again. And I think the point is that their velocities afterwards is such that C is bigger than B, is bigger than A, and they don't get any collisions. Right, let's go through all that again. So, momentum is your first thing. So, afterwards, VB plus VC has got to be equal to that plus that, which is 5.96 meters per second. Not so obvious which one's going to move the quicker. I think after the collision. No, yeah, that one's going to, VC's going to move the quicker, isn't it? VC minus VB is going to be equal to 0.4 coefficient of restitution times the difference between those, which is 0.2, 0.36. So 436 is 144 meters per second. Therefore, add them up, divide by 2 gives me VC, so that's 7.4 divided by 2.
Should be 0.144, I think. Is that right?
Yes. So 0.144. Yeah. VB, that one, take that one, divide by 2, is, it's all going a blur up, right?
Yeah, I'm the same.
What is it, Sam?
I'll just plug the numbers in. Just take, wasn't it, in this one?
Yeah. No, mine's that, divide by 2.
Oops, that's my decimal one, that worked. Because it's 2.908.
2.908 meters per second, right. Now we've got it. VC is moving faster than VB, which is moving faster than V8. They won't have another collision.
No, that's right.
Is there a quicker way of doing it?
No, I don't think so. What the space they go. Do they still add up to the 8? That's the other.
Oh, do they add up to 8?
They should, shouldn't they?
Please add up to 8.
Yeah, I think they do. just intuitively.
That goes to 60. That's probably what they do.
That's good. That's good.
It's a bit of reassurance there. Yeah, I'm not. Maybe it's you can reason that.
You can do it without calculation.
That you can do it without calculation.
It's
possibly.
pretty old, but
because we know that when B hits C for the first time, C is going to move faster than B, and therefore the next collision will be A hitting B.
yeah.
But then we need to, is B going to catch up with C or not?
Yeah. That's where you probably need to do calculations.
It's sort of hard to know because these are pretty similar. Yeah.
I think they expect the calculations.
Yeah, that was quite long.
Yeah.
So once you've got the idea, it's straightforward. Really, it's those two equations solving those.
I just wonder if you could comment a little bit more on why an inelastic collision results in the way they bounce off the way they do, more of a conceptual rather than a mathematical.
I mean, obviously the two extremes are the elastic and the inelastic. So what they've been doing here in that last part of the question, I assume that is the end of the question, is looking at that middle thing, neither elastic nor inelastic.
Oh, okay.
So elastic means energy is conserved. So so when you have an elastic collision, basically what happens is that the velocities of the two balls swap over if they're the same mass.
Newton's cradle plus up.
Yeah, exactly. Newton's cradle playing pools. Pool, the white ball is slightly less mass than the other one, so it comes out the other end when you pot it. But in snooker, if you're not putting any spin on the ball, you hit the ball head on, the object ball moves off, and the cue ball stays exactly where it is. That's an elastic collision. A way of looking at that kind of goes beyond what you do at school, is that when energy is conserved, you get time reversal symmetry.
Okay.
So in a system that conserves energy, you can kind of video record it, play the video backwards, and it will look the same.
That's cool.
That's kind of like those objects being thrown one up and dropping one down.
Yep.
You play that backwards and it looks
exactly the same.
And that's because you've got that energy conservation.
Okay.
So that's your elastic one. Your inelastic is where that ball hits that one, they stick together. So you've just got the two balls then move at exactly the same velocity afterwards.
Yep.
So
what do you call it when it's in between the two? Is it, we just call it like a...
I'm not sure, it's got a name. It's neither elastic nor inelastic. You specify a coefficient of restitution.
Yeah.
And so coefficient of restitution, so if sigma is 0, that's the situation here. The difference between the two is 0.
Sure,
so that's inelastic. Sigma equals 1 is elastic. The difference is the same.
Yep.
So forth.
That's it, because we don't... I've never actually thought of the in-betweens, because we've taught elastic collisions and inelastic, and how do you deal with all the in-between bits? And there it is.
Yeah, there it is. You use a coefficient of restitution. You have to have that other equation in there. You can't do it on momentum conservation alone.
Yep. So I think you're right that you do have to perform all the calculations to make sure everything's going in the direction it's supposed to. And you can sort of I don't know, maybe make a little bit of an assumption about which one's going to have the higher velocity. That seems to be the...
Yeah, because they've got the same mass.
Yeah.
You know, I know in this case, that second one's going to have a high velocity.
Yeah.
In this case, they're going to have the same velocity.
Yeah.
At no point is that first one, when they're the same mass, going to come out with a high velocity.
So it must be transferring. So
Yeah.
No, that's good.
So that
fills
we
all the
can
gaps, I think.
make that assumption fairly safely.
Yeah, no, that's cool.
But that's only because they're the same mass.
Yes, yeah. Good.
Otherwise you get a golf ball hitting a football
Awful.
and collision stuff.
Very good. That's a good one to finish on.
Okay.
Very good. Yeah.
That's the end of the scholarship 2012.
Yeah. Thank you very much.